Okay, so this is me. You have this. I guess you don't have the IG and Twitter, but so this is introductions. It was intended to take 15 minutes, so we have 2 minutes, but no problem. I formally did the first 2 parts, so they're prepared formally. The last part, I'm going to do a little off the cuff, but it's very recent to me, so it won't be a problem. So the next section, I intend to introduce the problem and in its generalities and specifics in the very basic case by 11. And then we will move into more complex cases. I don't know how familiar the group is with probability in general. Are you all familiar with probability theory? Sequences, Markov sequences? Okay, this is important. So if you already have that background, then it makes things a lot easier for understanding what I'm going to say. So, okay. So the next in the next section we'll do the complex patterns, Markov sequences, and the techniques for Markov sequences and handling nth occurrences, which I'll explain briefly. We'll take a break at 11:45 and then return to the advanced topics. So I'll relate what I said to these areas. So everything I do is going to be discrete probability, so discrete sequences. These techniques apply still to continuous underlying variables in discrete times. You just have to discretize the underlying continuous distributions. Understand that? We'll get into that. Scan statistics is an area you should be aware of because it's everything related to scan statistics can in principle be done in this theory, this area. So it reduces to this area. So however, there are specific techniques in scan statistics, which if you're interested, you can look into. And then in particular, complex underlying. So not just sequences, but multiple sequences, patterns in multiple sequences concurrently, and then space and time, right? So patterns in actual space and time as opposed to just linear and a temporal dimension. So I mentioned all this at the start to sort of, even though we're not going to get to this till the end, to say what I'm not going to do at first, right? Because I'm not going to do all of that right away, right? It'll be in the background of what I say in the first section, but when we actually do the math, it's going to be in terms of single discrete sequences. Okay. Okay, and so I'll get into the problem for AI architecture, which is maybe some of your interests in particular. And then this last bit is just a plug for everything I've kind of really been doing over the last year because it's a more general handling of everything in sort of one system. So okay, and then wrap up questions. But feel free to ask questions as we go. I mean, the group's not big, so I don't really need this particular section. So just ask questions as we go. Okay. So this is going to look a little complicated at first, but it's really not that complicated. So right in this section, this is just repeating the goals of this first section. And then this is what looks kind of complicated, right? It's all of these conditions on our system. So the idea is we're going to first do this in terms of sort of an operations research type problem, right? Where you have a system and you have to give a value for that system, right? The idea is you are going to implement a system that system has some sort of value, and then you are going to use that system, but you want to know the value of that system in principle in advance, right? Before you implement. So all of this is more or less embedded in this silly diagram here. So let me go over here. So the basic thing is you have some monitor, right? So a monitor is sort of a general name, right? We think of a monitor as like as a pantalla, no? But a monitor in like just somebody who's watching things, right? Making sure things are okay in security, say, or other areas, right? For operations. So first, we're just going to we're going to bundle that together, right? So they're all going to be one. So you have some sort of person, possibly with a pantalla, who's watching events, okay? And this person doesn't need to be here. So it could just be a computer, right? It could be a computer looking for patterns, who then, when something happens, right, they do something. Okay. So these are your recursos, your resources, right? These are units of resources, right? They're all the same. They might be soldiers, so they're sleeping, right? until you wake them up and deploy them, right? So you send them into the world, and then they go on some sort of mission, right? So they're going to go on some sort of mission. And these missions have some sort of value, right? That in principle we can quantify probabilistically. We don't know what's going to happen, right? But we have some sort of notion of expected value of the mission, right? When it happens. Okay. All right. So this is the basic setup. More or less, it's embedded in these principles, and you should have this PDF to look at if you want, right? So this is just the diagram I just drew is just this part here, right? So you have monitor, resource, deploy. That's the basic setup. And realistically, all of the mathematics, that's really what I want to address today, is here. Okay. So really everything is here. But I wanted to give it a context, right, for operations, right? And if I said this could just be a computer, it could also just be a human, right? And the human might have resources which are their actions, right? And they do them in the world, right? When patterns occur. So this is sort of an architecture for AI, right? You wait for patterns to occur, you do something, and then you wait again for another pattern to occur, and then you do something, etc. So that's how it's related to AI in generalities. Okay. So in particular, this model I've sort of targeted these cases, right? So you can think about this as sort of social infrastructure, right? La policía, the bomberos, no? Militar, no? They are monitoring events. They're waiting for patterns to occur. When the patterns occur, they notify the troops, the people, the military, the police, right? They deploy them to events in the world, right? Yeah.
Sorry, can I ask a question? Just to be sure I understand. The goal is to model the behavior of the person or a agent that takes the decision to implement, or the goal is to find a good policy strategy to
Both.
take the
The goal is
action.
both. The goal is both.
Okay.
Both, okay? So, the idea is, right, we have to model this process correctly in order to value this process entirely, right? That's the basic goal. So I'm going to really care less about this part of it, right? I'm going to give you a basic model of what this might look like, right? But realistically, mathematically, everything of interest is here for us, okay? So does that answer your question?
Both.
As we
you
go,
want
you'll get a better
to
idea.
model the behavior of, for example, the government taking actions after looking
Yeah, and it's very
events,
simplified,
or
yeah.
optimize the best government.
Well,
take those
so
actions.
this is a very simple model, right, of what's happening, right? In particular, we will only deal with one monitor, right?
Mhm.
So we're not gonna deal with teams of monitors,
Okay.
right? And then we're gonna assume that this one monitor will signal to the resources, right, what to do. And their missions have a certain value, right? And this system entirely, in principle, will have some value function, right? That's the idea. And now, to answer your question, if you want to optimize it, and we won't give the algorithms to do that, I'm assuming they will be in reinforcement learning and dynamic programming, right, in this area. But we want to give the value function of the basic missions, right? That's the basic idea. And to do that, we have to model this monitor behavior, right? That's the idea. So I give you in this PDF, we'll go over it briefly here, a model, very basic, for giving the value of the missions, and then relate them to the processes of the monitor, right? Because they are related to how frequent the patterns come up for the monitor, to say how frequent they will use the resources and the missions have value, right? So all of that will come together a little bit as we go, okay? Does that answer?
Yes.
Okay, good.
That's
So, one thing, and this is the hard part, which I don't really do from the operations research perspective, is that we're going to initially assume that you have resources and they all have, and arbitrarily many. So you have as many as you want, okay? So first we're gonna assume you have as many resources as you want, okay? The second thing is you can model this differently, right? And we'll get into this towards the end a little bit more, but you can model this differently where you have certain people you're paying to stay, right? And I call these, so if you draw the marker here, it would be the held resources, right? These are people you're paying every month to stay. But if you go over your limit, you might have an option to hire a contractor, right? Right? Other people to go out and do this. So these people would be on a lease, right? And in particular, these might have more different prices, right? So these would be fixed, right? But these would be more expensive, right? Usually the leased options as you need them would be more expensive, right? And you might have an option contract, which would be part of the fixed costs, right? So you have an option with some company, right, to always give you what you need as you need it. And you have to pay for that option in advance, right? So from the operations research perspective, right, the question is sort of how many people you want here, right, versus how many can you rely on here, right? And how much you would pay for this lease, right? Okay, so all of that is a complex issue, which initially we don't have to do to understand the importance of the monitor in general, right? So initially, we're going to assume this line is here, right? And you have either you know that you have enough resources just sitting around, right? Or you have only options where you have a contract for options and you pay for people as the missions arrive, or missions. So in particular, this doesn't need to be missions, right? It could be, I don't know, bundles of wheat, right? It could be tons of ore or something, right? Minerals. No, it could be really any resource.
Resources to be assigned to a mission in general.
Yeah, exactly. Yeah. So, but initially, we're going to assume these are all the same resource, and we're going to assume that they all have the same cost, and you have as many as you want, as many as you need as you go. Okay. So that'll come out in the model. I'll go over the model briefly, but if there's any questions about that setup, ask them now, because that's sort of the background for the importance of understanding the monitor. Okay.
Only the last question. Missions are variable in the amount of resources assigned to.
Yeah, the idea is, so
It's not a fixed.
yeah, you're getting, so you're right, and I'll do that right now.
Uh-huh.
Okay, you're correct. Yep. So, okay, it depends, right? You might only have one type of mission all the time, right?
Okay.
But you could have variable. Yeah.
The setup.
Yeah, it's adaptable.
Correct.
Okay. All right. So this is the unlimited option only, right? This is hard to read, but this is the fixed cost, right? And this is the fixed cost per mission per member, and this is the fixed cost of the. So I say cost. Yeah. So this is the overhead here. Ooh. Sorry. This is the cost of the monitor, and this is the cost of the mission, of the option on the mission. And so the overhead cost is the expected value involved in mission M, right, is what we're trying to do. Is an instance of resource allocation will depend on the deployment of resources required, the duration of the mission, right, the expected success and failure or false alarm of the mission, assuming we will not exhaust resources held. We have this formula. So this is the formula, assuming that we've never run out of resources, and all the resources are priced the same. Okay. So the basic idea is this is that expected value of the mission, right? This is the length of the mission, starting at t equals 0, t equals 1. You have a discount rate, right? So you're all familiar with discounting. So it's the process of the time value, right, of the resource. So okay. And then this is a sum over the outcomes. We're just going to assume success, failure, and a false alarm. Okay. And this is the probability of the outcome given the mission. I'm supposing here that you have historical data or some way of modeling. This is how I write conditional probability, right? You're familiar with conditional probability. So this is the conditional probability of the outcome given the mission. This is the value of the mission given the outcome. Okay. And this is the probability for how long it will take times the cost for the resource given the mission per unit time. Okay. Sorry, this is the RDM here actually is the number of units you need. So that's the number of units. The cost is here, right? So this is the cost per unit on a mission per unit time. And this is the number of resources you need given the mission. Okay. So, yeah, tell me. Professor, okay. Right. So LM is the max life of the mission, right? So we just suppose that if it reaches some time, we cut it off, call the resources back. That's it. And D is the discount factor, as I mentioned. Right. Number of units deployed is RDM, and this is the cost of a unit per deployment per unit time given a mission. And MACE, it may include such things as your possibility of losing the resource on the mission, right, or expending the resource. So this is called attrition, right? So if you send troops out to something, right, some of them might die, right? You won't get them back. So you have some sort of model, I'm assuming, of risk of losing people, right? Some expected loss, which you can put into the expected costs. That's what I'm saying, right? Okay. So the expected value of the system is then that expected value we just looked at above, included here, discounted by this factor dt, which is when actually it's from the time the mission gets deployed, right? So you have two discount factors. One is within the mission itself, right? And one is up to the time you deploy the mission, right? So you have to use that dt twice for that reason, right? So this is the expected value of the mission, right? Using the probability that you send somebody out at time t, right? You send a mission out at time t, right? You have some sort of expected value on that mission, and then you have the overhead total. So that's the overhead total. Okay. So this introduces something important, right? So this value, the probability of a mission at time t, is going to depend on the monitor, right? So we can represent that explicitly here by making the mission a function of the pattern.
That is the model of the monitor.
That's the model of the monitor, right? Well, it's the very basic use of the patterns, right? So you have this, right? You have this pattern set lambda I, right? And you have to sum over that probability of getting a lambda I at time t, right? Then that will tell you the mission, and you're still taking out the overhead. So just to be clear, in the initial case, this sum is going to be over not all patterns, but only the ones that include a mission, right? So you're going to have, so in a binary case, right, you might have patterns 0, 1, 1, 0, gamma 1, 1, 0, 1, gamma 0, 0, 0, 0, 1, 1, right? And these might be equal to some lambda r, right? So a constant r. And this would be one of our missions, but we might have, and then this lambda r, so you have this mission function now, which is going to take a pattern set, right, and return a particular mission, right? Okay. Now, you might have more than one of these, right? But each of these pattern I here, each of them is going to map to one mission, one type of mission, right? So we already know the costs and the values of that mission, right? So the question is, which of these lambda r we are going to hit? Well, lambda I, right? So lambda I, right, is going to be, in particular, a partition, right? A partition over the set of everything, which we might call lambda. I don't really like it. We're going to call A our domain, and we're going to say the length of, this is going to be the length, right? So in the end, you'll understand what I mean, but this is going to be equal to the union of the I, right? So the union of the I and mission. So there's going to be one set here. We're going to deal with fixed length patterns. So everything is going to have a fixed length. I do that for ease of the mathematics because I worked on this a lot, and it gets much harder with differing lengths. Just in terms of the indices, everything works out. It's just that there's a lot of extra indexing, right? When you deal with different lengths at the same time. So we're not going to really deal with that case, but I'll mention it. Okay. So there's going to be one lambda k, right, which is going to include everything that doesn't map to a mission, right? So this lambda k is going to be doesn't map, right, to mission, so is ignored. So you can look at this, the summation over I, right, in terms of looping over these different lambda r, right, these different lambdas, mapping to the different missions. But there's going to be one in here that we just ignore, right, which is the lambda k. That's everything the monitor just ignores and doesn't say anything, right? Does that make sense? Okay, good. Okay. So, first thing to note is this is a little ambiguous, okay? So, it depends on what we mean and what we count, so what the monitor is looking for. Okay. So here's the first problem, right, in the modeling of the monitor, is that suppose you have a mission, you have this sequence, right? The question is, suppose this maps to some lambda I, right? Some lambda, let's call it R1. The question is, how does our monitor operate, right? So there's two ways, basic ways, right? Our monitor might deploy things at this time, right after it sees this pattern based on where it is, right? What mission it maps to, and then skip ahead to this, right? Or it might deploy at this time when it hits this pattern, and deploy if it hits this pattern, right? And deploy if it hits this pattern, right? So that's sort of the first thing you need to be aware of, right? Your monitor matters. It matters how they're doing things, right? So if it hits this pattern and it skips ahead, that's going to be considerably different than if it hits this pattern, this pattern, this pattern, and this pattern, right? Because you're going to be deploying more resources. So, right, this phenomenon where you have 1, 0, 1, 0, 1, 0, 0, 1, and you have this region here, right, is to say that these patterns overlap, right? So is it the superposition? Okay. So you have overlap in this case, and overlap is what makes everything interesting. So really the overlap of the patterns is what makes everything interesting. Okay. All right, so let's keep going with the modeling of the whole system first, and then we'll get to the details of this. Okay. So the resources held only is pretty much the same, except it's cost per unit overhead, right? The fixed costs are going to involve the number of resources times the price of that resource, right? And then the function here is a little different, but it's pretty much the same. And then you have the same value equation. So in particular, this is a question, right? What is the probability that we exhaust our resources and when, right? So modeling of that distribution of exhausting resources is something I'm going to not solve, but it's solvable, right? But it's going to involve the nth pattern, nth occurrence distribution, which I'm not going to do too much with, but I'm going to point the way, right, to solving that problem. And then finally, we have the problem of mixed held and options. So I mentioned that prior, right? So the problem is that when you exhaust your held resources, you can option resources, but you have to do so at a higher cost. Some of that cost might be fixed in an option contract, right? And so you have to model that. And so this mixed option is probably the most frequent, right? And you need to be able to model the use of both, right? In a entire whole system value equation. So that's achievable, but it won't be our focus. Like I said, our monitor is going to be our principal focus. Okay. So this is what I'm not addressing going forward, right? With the monitor in particular, right? So identifying underlying basic statistical models from data. So we're going to, for the most part, assume that our sequences follow some fixed Markov distribution or some fixed IID distribution. Okay. So IID is independent and identically distributed, right? So it includes, right, the Bernoulli process as well as Poisson at fixed intervals. Okay. We're not going to be concerned with questions of like changing that model on the fly based on the data you have, right? We're just going to assume it's fixed. It's an important question, obviously, but still. Okay. We're not going to be concerned with finding patterns, right, that are good for sending missions, right? So we're going to assume that we already have the patterns too, right? The experts, right? You might just sit and watch an expert do something with a monitor and when they deploy resources and sort of learn when they make that deployment, right? And then construct patterns from their indicators, right? But we're not really going to deal with that, right? So we're not going to deal with the learning of the patterns. We're going to assume the patterns are fixed. The monitor, if it's a human, just has a job to look for the patterns, right? Which in principle could be coded, right? In terms of a computer, right? In computational terms. Okay. And we're not addressing questions of data monitoring. Systems are in need of more data or data resolution, right? So we're not going to. This is another point related to this. This is the learning of the patterns. And we're not going to be interested in doing what I just said, which is like if they're a human doing this, we're not going to be asking questions of how you can learn what patterns they're looking at. You might do that by supervised learning or reinforcement learning, but we're not going to be doing that. Okay. So in general,
I'm sorry, are you going to address the how many different techniques to search for this pattern?
So when the patterns occur, we're going to assume that the monitor finds them. So that's one thing, right? So the search you mentioned, the answer is yes, kind of. Okay, so we're going to get to that in the end in terms of the AI, where this matters in the AI architecture, right? As a hint, the idea is the agent will have a whole big store of patterns, but they need to prioritize them in order to use those patterns in time, right? By the time. So that's yeah, or the time will pass and they won't hit them, right? And you have to learn how to prioritize those patterns. That's really the biggest thing in the AI. Okay, so if your system works as the above pattern recognition-based resource allocator, and your monitor works in certain ways, which is what we're going to be discussing, right? Then your system may have a value which you do not correctly understand. Okay. So that's the biggest thing. And we'll get into it right now, but just to foreshadow a little bit, what's going to happen here is this PT lambda I is going to work if every time a pattern occurs, you allocate a resource on the IID system. On the Markov, it's a little, but on the ID system, this basic equation will work if what you're doing is sending a resource every time, right? Then you just need to know the probability of getting this pattern at a particular time, and this will give you the value. But for questions, and we'll get into that next, if you're splitting these, right, and not considering this middle pattern, then you will have to change the model. And moreover, if you want to know if you want to be able to answer the question of of running out of a resource, you're going to have to change the model. Okay. So this will work, like I said, if the distribution of the patterns is stationary, right? So it's the same at every t, or you know it at every t, and you're counting every occurrence, right? But it's not going to be a very general model. Right? So we'll get into the general model now.
The only way to take the intermediate pattern is in this way, or I could take the first three numbers and then one of the other patterns.
So you can take them however you want. We're assuming in this case, so I was assuming that 0, 1, 0, 0 was in this lambda k, which we're ignoring, right? I'm assuming that the 0, 0, 1, 1 is also in lambda k. We're just ignoring it, right? And so these are just patterns that get ignored. I'm just giving you an example where this is in a lambda, this is in a lambda that's relevant, and this is in a lambda that's relevant.
So the pattern is found, but not accepted.
And this pattern would be found, but we don't need it. We're just ignoring it.
Okay. The lambda k pattern.
It's what?
It's gonna be a part of the lambda k map.
Yeah, it'd be part of the lambda k map, which the monitor is just not doing anything, right? Yeah, that's the idea. Yeah. We'll get into more complex ways of doing this, but it's important to know, right? If they're doing it this way versus this way, things change, right? Okay. So if they're not considering overlap, things are going to change. For this model to work, they have to be considering overlap, and it would be the IID case.
Sorry, I have to go.
Okay, I'm sorry.
I'm
Okay,
sorry.
okay. So I mentioned also, so that RT is just mentioning the problem of running out of resources here. So I think that's it, and we can get to the math quickly here. This always takes longer than I expect, right? So I'm glad I didn't work out in full detail the last part, because we would never get to it all. All right. So the mathematical problem. So remember this, or take a picture or something, because I'm going to erase it. Do we have a eraser here? Professor Schroeder? If you don't, I'll just make do. I can use my hat. Please don't go. You can stay. Okay. All right. So I think I can get started, at least. So these are the goals of this section, this is a continuation of the prior goals, but this is the mathematical model, right? So we're going to start with something very simple, which is the coin flipping, right? This is just an IID model. It's uniform. And the question is how long you have to wait to get certain patterns, right? So that's the biggest question. So how long are we going to have to wait to get certain patterns? And it's a little surprising that on the IID model, even on the IID uniform model, you have to wait for some patterns longer than other patterns. Thank you. So, okay, so we have the ID model, and the question is how long we have to wait for a given pattern. So let me start by indicating what we're going to actually do here, right? So this is an IID model. We're familiar with the binomial model, right? So you would have some sort of some number t, and we are choosing one event, right? And then you have p1, and then you have 1 minus p t minus 1. And this would give us the probability of the existence of a single element, right? So it'd be a pattern, but it'd be a pattern of length 1, right? So if you just want to know the chance of getting an H, right? Right? So this, in general, we're going to write in terms of patterns. I'm going to distinguish now between patterns and words. So words are just single patterns. So say H, T is a single word. A pattern, a complex pattern is like what I showed you before. It's sets of words. Okay? So these are words. And if you have a word of length 1, right? If this word is length W equals 1, I'm going to use this notation here, LW, to indicate the length of the word. Okay. This is going to give you a model for what I write as this, right? Is just the probability that the word exists before or at t. Okay. And this is our model if it's length 1, right? And then we're familiar with the geometric distribution, which is going to give us the probability of the first occurrence of the word. I'm going to write that as t, right? And that's just going to be one of these, right? This is just giving us the probability that our first occurrence of the word, which is of length 1, is going to occur at time t. Okay. Does that make sense? So this I'm assuming you're all a little familiar with, right? So, but that's the setup Because when these change to length W greater than 1, we can't use this. This doesn't work anymore. So that's the biggest problem. Now there is a caveat to that. There is one analytic formula which is very big and combinatorial that works in some cases. But we're not going to get into that. Our methods are going to be more general, and they're going to rely on recursion. Okay. But that's sort of part of the setup. But I want to make clear that this is a problem, right? So, the other thing is we're going to write probability. So for an event of a pattern or a word occurring at t, we're going to write it like that. Okay. And so lambda I, the same. And I'll get into that. So that just means that that if you have a sequence H, T, H, 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 T, H, we can say this will be 1, 2, 3, 4, 5, 6, 7. And so you have, for instance, H dot 1, H dot 3, etc., right? And you have T dot 2, T dot 6, right? In this, right? We're going to mainly concern with in cases that keep going, but that's the idea. Okay. So that's the notation, right? These are the basic notational conventions I use, right? So it's, we can include W dot T. First occurrence exists and W dot T. Okay. Now, these models don't work, and I want to show you. All right. So we're considering a sequence of coin flips, and now we're going to consider when H is true, right? So for instance, for H to be true, H will be true at 5, and H will be true at 4, right? In this sequence. So that's the notation for words. Okay, tell me.
No, sorry,
Okay.
I want to.
Okay. And then TH, for instance, will be true at TH dot 3 and TH dot 7. Okay? So it's always at the end. You can think about it, if this is a time index, then it's when the pattern comes into being, you know? Okay. Okay. All right. So now, just to prove the point, right? We're going to consider sequences of length 3 and these patterns HH and HT, right? So HH is true in these patterns, right? HH is true in these patterns. It occurs at some index, right? So in particular, HH will occur here in this sequence of length 3. It'll occur here in this sequence of length 3. And it'll occur here twice in this sequence of length 3. Similarly, HT will occur here, 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 and here. But you notice it occurs in 4, right? And HH occurs in 3. So if we want to know the probability that HH exists by time 3, it's going to be lower than the probability that HT occurs by time 3. Okay. This also entails that we're more likely to be waiting still for HH than we are to be waiting for HT, right? And this is because HH overlaps with itself. Now, there's a lot of research actually on the importance in doing this for just HH or HHH or TTT or TTTTT, right? So these are called runs in the English literature. I don't know how you say this. Yeah, Koreas. Okay, so these are called runs. So this is an instance of a pattern that overlaps with itself. But of course, we've already seen this. HTH also overlaps with itself, right? So it's going to have a longer wait time, expected wait time. You're going to be expected to wait longer for this than you are for HHT. Yeah. Which is a little weird. It's a little bit counterintuitive, right? Because you might think we can just use this model or this model, and then consider the probability of getting another HT or TH, right? To get the probability of it occurring, but you can't. Yeah, you can't. Yeah. So that's the basic counterintuitive thing. If you know a little bit of probability, like if you ask an average person, they're going to say, yeah, it takes longer to see pattern things, right? Things that overlap, right? Things that form a pattern that have a period. You're going to, an average person, yeah, they're more informative, they're more interesting, right? You expect to wait longer. But if you think about the model and then you think about this, you think, well, why doesn't it work, right? And it doesn't. It doesn't. Okay. So one thing is, in all of this doesn't somehow go away if you have a Markov distribution, right? It doesn't disappear. So even in the Markov case, you can't consider the probability of getting the first letter, right, at some time t minus the length plus 1, and then getting the remainder based on the Markov one. Doesn't work that way. Yeah. So you have to consider the overlap of the patterns. Okay.
Sorry, a question just to be sure.
Yeah.
This problem is only due to the fact you are using a sliding window through a single chain of states, for example. But if you have a fixed window that is no overlapping, there's no problem, and those models.
Yeah,
Okay.
so it's a little more complicated than that. But if I understand you correctly, the answer is yes. Because, right, if what you're considering is, again, so let's say the length of the words is equal to 2, and you're considering HH, H, T, H, T, T, right? Then this, right? This, and then also we need TH, and we need TT, right? This and this is effectively a binomial model, right? Right, if you're just considering intervals like that, right? Yeah.
But if you have a sliding window with a step of 1,
Well, don't think about it that way, because even in this case, right? If these are somehow what you get, right? So you have pattern 1, pattern 2, pattern 2, pattern 3, pattern 4, then you could consider this pattern, and in the data, you would wait longer for that, right? If you're considering these as one event, right, then you can reduce it to a binomial model, and then this would work, right? So if you're considering like the distribution of letters, right? In a text, right? Well, they're going to be reduced to some binomial, some binary notation, right? For the letter, right? But they're going to be considered independent. But then if you consider the words, right? Right, you're gonna have to consider the whole the probability of the word occurring, and for that, this model doesn't work.
Oh.
Okay. Okay. All right. So we're gonna get into some fun tricks here. Like, I think this is really cool. So. So I couldn't recover my image. So, but let's look at the table. So go here, go here. So this was my master's thesis now too long ago. Sorry, I didn't have it there. So this was my original master's thesis. I did it at Paul under Massimo Di Piero, who's currently at SpaceX. And he knew I was working on this problem in patterns, and he suggested we make it into a contract for finance, so people could pay for, under some value, a contract where it gave you money when this pattern occurred. It's a type of option. So I did this under him at the Paul, where I have my master's in computational finance. But I was working on it before that. He suggested we make it into a contract. He actually did this table too. Which I can find it. Okay. So these are the frequencies of occurrence, right? If we just used a brute force approach, right, to get the frequency of occurrence. So these are like it's n, but it's the time t, right? So it's the time in which you have for it to occur. And you can see in the UU case, right, you have this for a probability of it occurring at some time. Whereas in the non-overlapping case, you have a different probability. Of course, it's a uniform model, right? We're just doing a brute force approach, so these are the same, right? But you can see that the difference is given by the time and the overlap. Okay, so this is clear. Let me just keep this. Okay. So the distribution, right, the cumulative distribution for the existence, right, then is going to look something like this in the, right, this is where this is t equals length of w, right, and these are the various t. And if it overlaps, this will be the non-overlapping. If it overlaps, it's going to be a little slower to grow, right? And this is overlap, right? So this is what it looks like if you're just considering overlap versus non-overlapping, right? Well, this is the probability that it exists by t. So this would be the probability of lambda, but I can say words in this case. Word exists by times t, right? So this is the cumulative distribution of the probability W exists for the first time at t, right? And that's the basic picture we have in general, right? For words. The same pattern occurs with complex patterns, right? So it's the same idea for complex patterns, but you have a more complex answer. Okay. So I don't need this. So let's go here.
Sorry,
So,
up to this point, those results you're showing there are just from frequentist approach, just counting and seeing.
that's correct. So this would only necessarily hold in a uniform binary model. Yeah. So this is only going to necessarily hold in a uniform binary model. On the graphs, I should say. But overlap always has an influence, right? Even when it doesn't look like this, right? So you might have a pattern that overlaps with itself, say H, right? And it would be like this HT. But if H is much more probable, right? So if the probability of H dot T is greater than the probability of T dot T, right? Then this overlap might be higher, but then this line might be higher, right? But the influence of the overlap doesn't go away. Okay, so it's still not as high as it would be if it didn't overlap, right? So there's still an influence on the line, but this is the uniform, and I shouldn't say binary. I should say just the uniform. Okay, and the influence just doesn't go away. Okay. So to see that, back to where it was. This is it. Okay. So I'll get into that later. I'll get into that in the markup section. That it still matters. Okay. So now is a bit of the fun part. So this is the plot that I was going to show. I was going to show it in a different way, but I can do that in a moment. So we need a way of representing this overlap, right? And so the way to do it, and it's the best way for generality, I'm going to erase this now, but I'll put up a different picture like this in a moment. Kind of leave it, I suppose. Leave it like that for now. So we're running a little late, but that's okay. All right. So for a pattern, H, T, H, H, we're going to give what is called the signature of the pattern, right? It's the signature of the overlap. and it's going to be represented as 1, 0, 0, 1. Right? So what does this mean? Well, sorry, let's do this, let's do it here, overlaps with itself entirely, right? And so that's this first one. Okay. Now, if you shift this, where does it overlap with itself next? Well, it doesn't overlap here, so that's the 0. It doesn't overlap here, that's 0, but it overlaps here. So you have H, T, H, H. Understood?
It's an encoding for the
It's an
overlapping.
encoding for the overlap string. Yeah. So let's back this up a little bit. Let's do a slightly more interesting example. All right. If you have, for instance, H, T, H, H, T, H, H, T, H, H, T, you have what are effectively periods here, and then a tail. So what you get is 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. And you have to check because it doesn't overlap at T. So this is going to be a 1. This should be 0, and then a 1, and then a 0. Like that. So if you took this, right, and you shifted here, it fits, right? You shift it here, it fits. You shift it here, it fits, and then it doesn't overlap at the tail. Okay. There are some interesting properties with this, like this periodic property, because what actually happens is you have this period property for the whole string, and then you have to consider the period property of this string, right, to figure out this on the table. So it's kind of an interesting thing, because if we kept going, right, to H, right, well, it's going to fit here on the period, but then this itself has a semi-period here, right, and it's going to overlap with itself here, so you get an extra 1, right? So this recursive periodicity property is important, but this is the idea of the overlap signature. Okay. So
Sorry, when are we assuming that first element will be a 1?
in this case,
It overlaps with itself.
yeah, because this period, if you just consider this one, HTH, right? It's got a semi-period, it's called, right? And it overlaps with itself here, so you get 1, 0, 1. But you'll notice if you shift this, it doesn't fit here, it doesn't fit here, right? It doesn't fit here. It only fits on the tail. So this is a little, but there's a systematic way of doing it, right, with the periods. Yeah. Okay. So there's a sense in which we don't really need this one, right? Because we're only concerned with the overlap, and then we don't need these. But this has a really interesting property. So we'll get into that now. Let's see if I say anything first before I get into that. So the first interesting thing is, and I just give you a long example for kicks, but if we actually consider all of the overlap strings themselves, on the uniform model, they're all going to have the same curve, right? So there's only a few, right? In the case of length 4. 1, 0, 0, 0 is possible. 1, 0, 1, 0 is possible, and that's it. It's not possible to have 1, 0, oh, sorry, I missed one. 1, 1, 1, 1, right? That's the run. Yeah, the run. It's going to match everywhere, right? So it's not possible, though, to get 1, 0, 1, 1, because if it matches with itself here, then it would actually end up matching with itself here. So not all patterns, not all binary strings represent patterns, right? Okay. But if you consider these are actually ordered, and you can get this diagram with 4 curves, right, from this, right? So if you consider this to be 1, 0, 0, 0, right? You consider, we'll start at the bottom here. This will be 1, 1, 1, 1. Then you would have another in the middle, and yet another underneath. These always go to 1, right? And this one, they're actually ordered by their signatures. So this is actually going to be closer to 1, 1, 1. This is going to be 1, 0, 1, 0. And this is actually going to be the one closer to 1, 0, 0, 0. 1, 0, 0, 1. So the first interesting property of the signature, if you include the leading one, is that you can order these, right? By just their signatures. Okay?
Interpreting that as a binary number.
Yeah, just representing it as right, reading it as a binary number. We're going to also use them as vectors because we're going to need to know where the overlap are in our equations. But using it as a binary number, yes, this is exactly what I'm doing here, right? If you read it as a binary number, you can order them by their signatures.
It tells you the degree of overlap.
Yep. Yep, and so there's a degree of overlap which is greater in this case than this case, even though there is overlap and only one location. Yeah. Okay. And it continues like this, right? So if you have patterns of 10, like 10, right? You get a multitude of different patterns, of different signatures, but they're all ordered by their overlap signature in this fashion.
And that is a conjecture, or it is shown that
I can prove it. I'm not going to do it here, but I can prove it. I can prove it.
there is a proof.
Yeah, I have it. Yeah. Yep. Yep. And it gets better. So, so wait. So, all right. So now the magic, right? So the magic is this. If you suppose your domain is uniform HT, right? Then you're going to have this is going to be a cardinality of 2, and in this case, if you want to know the wait time, the expected wait time for this. It's 1, 0, 0, 1, 0, reading this as a binary number. For this, it's 1, 0, 0, 0, 0, read as a binary number. And this is going to be the same, 0, 1, 0, 0, an extra 0 in every case. Binary number, 1, 1, 1, 1, 0 as a binary number. And that's your expected wait time. Read as a binary number.
Dividing by 2.
Read, not dividing by 2, but reading this as a binary number. So if you spell this out, right, it's going to be 2 to the 0, right? 2 to the 1. Yeah, we just shift this left. It's going to be plus 2 to the 2, right? Plus 2 to the 3, plus 2 to the 4. And that's your expected wait time. Where this one cancels. And it works for every base. So it doesn't matter how many things you have in this domain, right? We're going to call the domain here H. We're going to actually call it A, right? And it's going to have some length, some size, right? Which we call this. So whatever your signature, if you have a signature of a word, you can multiply it, read as a number, right? So if we read this as a number, 2 times the, I'll call this the base, right? Right, the length will be the base. This formula gives you your wait time. So you just take the signature, you shift it, adding a 0, you read it as a number in that base, and you have the wait time. The expected wait time. It's kind of a miracle, right? It's kind of like, why is that, right? I know, believe me, I know, it's kind of a miracle, but you can prove it.
It makes sense because it's true.
Yeah.
With all the patterns.
With well, it's true for the uniform distribution. Yeah, the uniform distribution. So there are tricks to get it to work with the binomial and distribution more generally, right? But you have to do some extra fancy work, and you need to But it's kind of a party trick, right? You can write out a long string, A, B, C, A, D, and if it's not overlapping, then it's just 1, 2, 3, 4, 5, 6, right? So it's going to be 2 to the 6 is going to be the wait time, right? If this is not binary. Suppose there's it's going to be 2 to the base, right? The base. Yeah. Whatever the domain is. Yeah. It's cool. Yeah. All right. So to give the proof, which I won't do here, you have to consider that this is a delayed renewal process. So I'm not going to get too much into renewal processes, but a renewal process is like so the basic example of the renewal process is the exponential distribution, right? Because if you choose any time in the exponential distribution, it sort of restarts and does the same thing again, right? So if you're waiting for something on an exponential distribution, you choose a time, while it restarts, and you have the same distribution for waiting more, right?
Mm-hmm.
Okay, so these patterns in the uniform case follow that same model, where it'll restart. In fact, in every case, it'll be a delayed renewal process. And it will restart after the length of the pattern minus 1, and have the same distribution every time. It's delayed because you have that wait, right? But it's the same once you get there. So,
Sorry, I have a meeting with one of my bosses, but I'll be back
oh, that's fine.
then.
Sure, okay. We have time. So I'm going to quickly go over the basic algorithm, and then we'll probably take a break because we're already getting up against our limit here. We've already blew in the budget by 30 minutes. So, okay. So these are the basic algorithms, right, for calculating the wait times, and the existence formula. We don't, So if it doesn't overlap with itself, this is the probability of the first occurrence of W at t, right? It's just going to be the probability of the occurrence at t minus the probability that it didn't exist prior. If it doesn't overlap with itself. If it does overlap with itself, you get something a little uglier, because you need this special term. This is where we use the sigma function, the signature, right? We're using it here as a vector. And if it's 1, right, then we multiply by this probability, the probability that it occurs for the first time in the overlap region. But the same, it's the same formula here as here, but you need this, what I call the POV, so you'll see this in the future. The POV, which is the probability of the first occurrence of W in the overlap with itself. And you take that out, and that gives you the probability of the first occurrence, and then you can just use it in this same formula. So these are basic algorithms. It's originally due to Gunnar Blum. He's in Sweden, I think. I think he's still alive. He did this in the 80s. The reference is actually in that PDF, which is at cschroeder.com. And now the monitor, right? So let's discuss quickly the importance of this, right? So read this. Yeah, so we haven't done a whole lot with patterns yet. We will get into it more. We know that a certain before we said there was a certain ambiguity in this, right? We now know that the statement is equated with the pattern just existing, right? If you're counting every occurrence, right? So we're not using any of my mechanics. You don't really need it. But depending on the monitor, right, you do. So if you skip ahead and you start looking for patterns after the last pattern, then the monitor changes, right? Right, so it is quite possible that our monitor, once it deploys resources, will ignore subsequent overlapping instances, at least for a time, rather than redeploying more resources, right? So if we have one case of DDD, right? So danger, 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 right? So we're looking for a run of dangers, right? Because if you have a run of dangers, you think there's a real problem, right? So you're going to send it. Well, if we get one more D, we might not want to send resources right away. We're going to say they ran away, they sent the resources already on this problem, and you're just going to wait for those people to get back to us, right? So in that case, right, you're going to have this parameter Y, right, which we're now going to split the original equation. So the original value equation had this part and this part, the overhead together. We're going to ignore the overhead equation, right? But now we need to model just that first term in the value equation. And we would do that with a recursive call to the value equation, but at a offset of Y, which is, so we deployed resources, now we're just going to sit there for a while. And we're going to check back at time Y to see if they need more resources or not, right? If the problem's fixed, we don't keep sending resources. That's the basic idea of this.
So in that case, the moving the sliding window that we have for the pattern, we want to force that padding of the length of the work, so we don't actually send more resources.
Right, so in that case, so notice in this equation though, we're not considering the probability of all, we're considering the probability of the first occurrence. So we're waiting for that first occurrence of D, right? Then we're going to multiply that by the expected value of the mission, but then we're going to rely on a recursive call to the value equation, right? Which is at an offset of Y later in the future. Yeah. And so that's the recursive form where you have some weight. And so this Y in particular might just be the length, right? And that would give you the case, again, where you had 0, 0, 1, 1, 1, 0, 1, 0, where you consider just this. So you can model this case with this equation if you just set Y equal to the length of W. So you have these formulas, you can go back and look at them, right? So, but that's the basic idea, and this helps. Obviously, right? The probability of the first occurrence here will help because it allows us to time the deployments when there's offset. Okay, I think that's about it. And so let's take a quick break. Is that all right? Okay. But if there are any questions about this, ask them now, because the next section is just going to build on everything that we did so far. Okay. We can break until 10 minutes. Oh, awesome. What I didn't mention, it's kind of obvious, right? But on this model, any word that has, on the uniform model, any word that is longer than another word will always have a longer wait time, right? It's kind of obvious it follows from this. Just keep that in mind. That's not the case on a general binomial, right? Because if you have high probabilities for some words, that they could be more frequent if they're longer, even if they're longer. Right? Okay. All right. So, all right. Let's keep it in. This up here. Okay. So complex patterns. So I already introduced these, right, in the first section on the monitor in general, right? So the basic idea is you don't have a single word, but you have sets of words, right? I should say I1, I2, right. W, I, down, lambda, lambda. This is pretty good. Okay. And I use the length W for the length of a word. We can use it also for the length of the pattern because we're using fixed length patterns, right? They're all going to be the same length. Like I said, it's not necessary, but it makes things easier. So so we'll use this same notation for the length of the pattern, and then we'll reserve this, right, for the size of the pattern, right, the number of patterns. Okay. So we're going to do basically the same thing and use the same notation, right? We're going to have lambda I dot t, right, probability, and I first occurrence, t probability, lambda I exists, t. We will soon introduce one more thing, which is probability of lambda I t. It's the same as this, but it's going to be n. So this is the probability that there are at least n occurrences, right? So there are effectively greater than n occurrences, greater than or equal occurrences. Okay. Okay, so really things are not conceptually that much difficult, but you have a complexity problem algorithmically once you start using large sets of patterns, right? So it can get We won't do too much with runtimes. I have another paper which I haven't yet published, which I do. I need to change the notation because I like this notation better than the one that is used in the literature, and I use the one in the literature in that other paper. But I'm going to change it to this notation just because it's easier to think about. And then I can make it available, that particular one. But it's an algorithmic paper mainly. But I do a lot of work on proving the complexities. So the basic introduction is this, right? So we have we just have this event, right? The lambda dot t is going to imply that some word w in the pattern is going to occur at t. And the probability is just going to be the sum of those events. And that's possible, right? Because they're all fixed length patterns, fixed length words, right? So the sets are going to be mutually exclusive, right? So each pattern in the set is going to be mutually exclusive. The sets, the elements in the lambda I are mutually exclusive, right? They can't occur both at the same time. And so that's a large part of the problem. If you have, or part of the problem, if you have complex sets of different lengths, they can occur at the same time. You have to get rid of some patterns for some algorithms. You have to keep those patterns for other algorithms, right? So it's a little bit more challenging with mixed length patterns. But if they're all the same length, then they're mutually exclusive. And if the lambda I form a partition, like I said, the individual lambda I are also going to be mutually exclusive, right? So J. And so if we wanted to know them together, we would just if we wanted to know the probability of this or this, right, we can just sum over each of them individually. But that's just for the probability of occurring at a particular time on a stationary model for the patterns, so the IID model. And we need to do more work for the Markov case, which we'll get to, but we can show the basic algorithmic update now. So the problem is, the first problem with this is that we don't just have the overlap of a single pattern, right? You need to consider the overlap of the patterns together, right? Different patterns, right? So in particular, right, you have this HH, TTH, TH, and then we'll consider what that value of the overlap vector is, right, at a particular location. This overlap vector is going to come out different, right? Because you're going to have a 0 in the leading position if they're not the same, right? If they're not the same pattern. And then you're going to have this. And the interpretation of that mathematically in terms of expectations, I'm not going to get into, but there is a relevant interpretation. Okay. And so in some cases, you can use that relevant interpretation to construct the expected wait times for complex patterns as well. That's more algorithmic. Okay. All right. So here, this is pretty much the same, right? We're just going to sum up the values of first occurrences at t, but notice we have this parameter lambda, which is telling us what the relevant set is. So I say lambda, if I'm talking about a generic pattern, any set, I'll use lambda. If I should, when I'm talking about the universe of all patterns, right, reference it like this, right, lambda would be the length of the word, right, the set of all of these patterns. Okay. All right. And so the probability of first occurrence is pretty much the same in its form, right? You have minus length of the word. probability of the pattern occurring, but then you have this other POV value, and for that, you need the signature of more than one pattern with itself. You're going to have to consider the probability of different words together, right? So in particular, we're summing over, this is W1, W2 in lambda, right? To get this POV value that we have to then take out of the initial one. If it happens to be the case that none of the patterns overlap with each other in any direction at all, et cetera, then you don't need that, and you can just use this first term. But that's rarely the case, right? With complex patterns in particular, they at least overlap on one character normally, right? Something like that. Okay. And so this here is our new probability of first occurrence. So this is probably a first occurrence without the lambda, but this is first occurrence of W and not a prior occurrence of lambda. Right. And so we need to calculate that, and we give that here. And it's a little more technical because we have to consider some things. We'll get into that. So in this case, probability of W, we notice we're just passing W prime here from lambda in the first prior positions, right? So if any of these overlap with W, then we have to take out that probability, right? To get the uniform probability of just the word, right? Of just the word. So effectively what this says, and I think I get to it here, but I don't know if I get to it here. Maybe I do it in another section. Yeah, it's in the Markov case. But notice what this actually says, right? It says probability of, Oh, this is the more general form. So not a particular word, but just words in lambda I, right? So there's two forms of this special equation, right? One is we have a background set, and this is the subset, and then we're concerned with this taking out just we're only concerned with the occurrence I, but we have to take out all of the lambdas. That's the generalization on the prior version of the form. Okay. Notice that this form says, right, so if you have lambda I first occurrence T, this is going to be probability of lambda I at T and not lambda exists T minus 1. Right, so it's a logical expression for this. We're going to have to use this form in the Markov case. So I mentioned it here. So these are equal. Yeah, so this is how you should think about this lambda here, right? So it's not occurring. Obviously, if this is just lambda I, then we don't need to put that there. It's the same in this part. Okay. And now, in that context, we were only concerned with a single target pattern, DED, but we can modify the formula. We're going to do the same thing as we did before, right? But now we're going to use this lambda slash lambda k, where lambda is actually the universe. So I'm making this a little more complicated, but And it probably needs to be. Lambda in this case would be the universe, the A, L, W, right? In this case, where we're doing this slash. So this lambda, right, and where we take it out. So what this is the difference of lambda, the universe, and the lambda k, right? Because we're getting rid of the lambda k. It's the ones we ignore. It's a formal expression of what I implied in the prior. I probably should have included it, but okay. So what we're saying here is, right, we need the probability of the pattern occurring. We need the mission that happens when that complex pattern occurs, right? And then we're going to make this recursive call. It's implied that we're passing the same lambda I to the value equation, right? The same set of the same partition to the lambda equation. To the v equation. It's the same partition on the recursive call. Okay. That is fairly straightforward, right? And the runtime's not so bad. But finally, we get to the Markov case. So you're all familiar enough with Markov processes?
No.
No? Okay. So the ones we'll deal with are order one. And it's a very simple idea, right? It's just the probability of an event at t, which in the IID case, we could write as lambda dot t, right? We now need to conditionalize on the past, right? So this is no longer going to be the same in every case. It's going to depend on the past. And in particular, it's going to pretend so this is the IID, right? It was stationary. So same everywhere, right? But now it's going to be, we're going to need effectively lambda dot t conditional on some word, a prefix. Let's do this, dot 0, right, which is going to be like a prefix. But the Markov process is the same. You can do it in terms of any domain, A, B, C, A, D, F, B, C, right, etc. It'd be some sequence like this. So it's going to look the same. But instead of the probability being the same at every t for these letters, or having the same probability if it's not uniform but binomial, right? It's going to depend on the prior letter, right? So we're going to write this, we can write it as probability of b dot t conditional on a dot t minus 1, right? And this is going to be our distribution in general, right? So if the variable, in terms of variables, we can write x, right? T.
Depends
Yeah, we can
on
write
the
it.
actual state and not the history.
Yeah, x, right? So some x t prime, right? Conditional on x t prime minus 1 t. So this distribution is going to be the same at every location, right? But that means that if we have some prefix, some start to the sequence, these sequences are going to be different, have different probabilities, depending on this W0, right? Because you get a different probability of that, and that, and that. So if the W changes, you're going to get a different probability. And moreover, you're going to get a different probability at each different T, right? So it's a bit more of a complicated process. Markov's, if you don't know it already, you need to do some studying because it's important in probability at least, okay?
This is a solution for the overlaps. probability.
This
For
is,
example, if I don't use markup, I won't have the probability to appear a new overlap in the process or not.
we'll address this now. You're still gonna be able to do it, but you just won't be able to use the fixed value of lambda dot t. You're gonna have to use the probability of lambda I dot t conditional on some word w, 0, right? And in the model, it's going to depend really just on the previous, the probability of the term before it, right? So lambda I dot t conditional on lambda I dot t minus 1. But conditionalizing on patterns doesn't really work. So we have to break this up into different probabilities, and we'll address that now. But that's the basic idea, right? You have these step probabilities. So the probability at a given time won't be the same as it was at some other time in most cases, unless the distribution is in a stationary state. We're not going to get to that. But it's going to depend on the prefix W0. And given the prefix W0, so we can calculate this just from the Markov distribution. So this we can get. This is not really the problem. If you have a Markov matrix, right, you have an initial condition W0, which in the underlying Markov will just be the first relevant character. So in Python notation, it'd be the last character in the word, right? You can recover this probability. We won't talk too much about that. I'm going to kind of assume that. But you should know that we can calculate this, where this is a word, and it's really just the letter in Python notation, be the last character minus 1 that matters to get the probability at some time t. The probability in the overlap is a little more delicate, right? Will depend on more things, different positions in the word, right? If you're at a time t less than the length of the word, right? And you have some word, we'll address that now. Okay.
Doesn't it just reset that you said before? The exponential distribution?
I'm sorry?
Doesn't it just reset the probability given that word, like you said in the exponential distribution?
Yeah, it resets the probability, but the underlying is not an IAD model, so you get a different dynamic, right? So you still have the renewal property, but it's a different distribution for the lambda dot t. So we'll talk about that a little bit. But this first part here in Markov sequences, you don't have this. If you're interested, I can make it available. But basically what I'm saying is, right, so if we started off with our heads, tails, right, and we just had a uniform distribution on heads and tails, right, where the Markov distribution is could be, one Markov distribution can look like this, right, where we instead have a different probability conditional on t, right? So if this is the probability of h at some time t, right, then this is the probability of, and this is the condition that t exists at t minus 1, then we can set this to d minus 0.5 minus d. We can set this, right, the probability of t to 0.5 plus d, and this is a consistent distribution. Well, okay, if we do that, if you go back to our initial case, right, and these d's are small enough, nothing's going to change. You're still going to have a higher probability of getting each t. So this is the reduced form, but I have an extra parentheses in there. But that looks right. So ignore that last parenthesis. But these are the probabilities. This has effectively 1, 2, 3 terms. But this distribution is small. So anyway, In any case, this is going to have a smaller probability of this if the D is small enough. So overlap still matters. It's just less obvious how it matters, right? It just it occludes things. Okay. But I give this simple example just so you can plug in a D and see the numbers and they don't change a lot. Okay. They're going to be very, if they make it small enough, it's very close to the original and those differences are going to be the same. All right. So given a Markov distribution on a domain, an initial condition, or a distribution over initial conditions, it is a simple matter to calculate P dot T and therefore lambda dot T, assuming one has a matrix form for a distribution M. This is given by the probability. Right. So here, okay, where recover from the transition matrix. So here we're using a Markov matrix. So this is a Markov matrix. We're just pushing it forward and we're using initial conditions, right, to get the distribution over letters, right? And by that method, we can get the relevant conditional distribution of a word W at T. And this should be dot T here. And it's, no, it shouldn't be dot T, but this is the distribution at T for W, right? It's going to be depend on the word, right? Conditional on the word and the probability distribution of that. So it's pretty much a simple matter. Once you have the Markov distribution, to calculate the probability of lambda dot T conditional on the word. So that's not going to be our concern. Our concern is with the algorithm. Right. Okay, so the first thing I know here, right, is that if our domain is small enough and the pattern length is small enough, let me use this space here. One can actually set up a transition matrix for the patterns themselves. And in that case, it's fairly straightforward to calculate the probability of first occurrence and the probability of existence. So in particular, right, so if we have just H and T as our domain, and we're concerned with patterns of length 2, H, T, right? So patterns of length 2, let's write it, L2, right? Then you can set up a matrix and get the probability of, for instance, H conditional on H, T, this one's going to be 0. Notice that we go in the yeah, it's going to be 0 because we're concerned about the overlap H, T, right? And so to write this in sort of order, right? H, T, H, H is not a valid sequence, right? So this probability is going to be 0. But if you have instead, right, the probability of, right, TH, right, then you're going to get a sequence H, T, T, H, right? And so conditional on this event, this is going to be equal to the probability of H conditional on T, right? And that's for the patterns, right, of length 2. Sorry, so we're dealing with patterns here, so we can set up a Markov matrix and recover it from the original Markov matrix. So there's two matrices, one for patterns and one for the underlying events. So this is a simple matter to do, right? If the length is small and the domain is small. If it's not, then you have a big problem. So we deal with the more general case, but it's important to know that you can do that. And then there's a simple method, right? So if you set up the matrix and then you just include sync states. So these are effectively, right? You start with you have the full pattern matrix here, but then these are the patterns that you are concerned with, the ones in lambda I. You can actually construct, once you have the pattern matrix, you can multiply this, right? So this can be M lambda I, where this is the full pattern matrix, but you subtract out this pattern matrix and make them sync states. And then once you do that, you get accumulation of the probabilities here. And so you know the timing of the events. That's a simple way to do it, but often it doesn't work, right? Because you have too many things in your domain and you have too many, too long of the pattern. The patterns are too long, right? So the matrix would be very big, right? And very too big in most cases, right? Because you can consider, right? It's the size of the matrix is going to be, right? The number of words, so the number of patterns, right, is going to be our domain, right, to the length of the word. And then to use the matrix, obviously, you need to do this squared, right? And so once the length of the word is 5, right, you get 10, say to the base 10, things get big already, so in a hurry, okay? So, but you should know that you can do this, right? And make sync states for the patterns, and then push roll the matrix forward, calculate the values, and that's one simple, probably the simplest way to do it. The other way is just to remove these and take 1 minus the sum of the residual probabilities. It's a sort of complement method. But that's a fine method, like I said, if you have small patterns and a small domain. But the more general case is more complicated if you want to have computational feasibility. So that's what we're addressing here. All right. So our original form was this, right? So the original form for the first occurrence of lambda at t, we had this, which is the non-overlapping case, and then we have the subtracting out the probability of occurrence in the overlap, probably the first occurrence in the overlap. But we need to calculate this. And in the Markov case, we actually have to calculate this. So the problem is, first of all, that this value, conditional on W0, isn't really what we want, right? So even if we have a prefix to this Markov chain, right? We need to have it conditional on this event, right? Or the negation of that event, rather, right? It's got to be conditional on the negation of that event to get the probability there. And that's a little bit more complicated matter that we can address. And then further, we note that this value here in the value equation will need to be conditional on an initial condition, and this condition will need to change depending on the lambda I that we are considering. So effectively, the problem is that in this recursive call, right, we need to know what pattern we are going to conditionalize this event on. And conditionalizing on a pattern doesn't really work. Okay. So we basically have to loop over all the words. We have to do this one by one for the words. So let's, condition, WI is the initial condition. Right, so we have this WI, which occurs at 0, it's the prefix to our sequence. We're going to assume that we have that. You can use a distribution over the words too, but we're going to use some probability to figure out what this value is. Right, so in particular, I erased it, but this is what I wrote before. It's the probability of WT and not the pattern, right, prior, conditional on the initial condition W0. We can use the law of total probability. We know that this event is equal to this event plus this event. That is, it's equal to the event with the conjunction of the negation, an event with the conjunction of the original event. Right? That's the law of total probability. And then rearranging, we finally get this formula. And then this, we can calculate directly from the matrix. Right? That was by the method discussed prior. And then this, we can actually calculate. So it's not the event that we want, but we can calculate an event that matters, right? And that will give us what we really want. Okay. So to calculate that, we use this. So we loop over all the words, we consider the probabilities of first occurrence, because here we're concerned with the existence. So we're concerned with WT existing, or W existing at T, and then lambda existing everywhere prior, or not everywhere, but somewhere prior, right? So we're going to loop over the lambda, the items in lambda, and consider their first occurrence, and then consider multiplying that by the probability of WT given the prefix at W prime times W prime at T prime. So that's the basic formula. There's a little bit of a catch, which I'm not involving or not considering here. It's that when the T is really close to the prefix, then you get a triple overlap problem. And so you have to handle that formally, and I do that elsewhere, but we're going to skip that part for now.
And so in that term, when W prime equals W, and then the probability is 1, right?
When W prime,
Like we're searching for that same prefix as the one we're currently looking for.
so this here is effectively the same form as this, right? So it's like a recursive. This is a recursive call, but it's valid because this T and this T prime. So if you consider, this is really just W dot, I should have probably written it that way. It's equal to the W at T minus T prime conditional on W prime at 0. Yeah. Yeah. So this is actually a recursive call. Right? And like I said, there's one caveat to all of this, is that you have to be a little careful when you're too close to the original prefix, because you get a triple overlap. And then once you have that equation, it's much easier. These W first occurrence at T are going to be are going to be mutually exclusive events, right? So you can just sum up their probabilities. And that will give you the probability of first occurrence of lambda at t. And that's all you need. You can obviously get the existence too, just by summing over that, the different t. Sorry, this one's a slightly more complicated scenario, but it works. So I will make this available just because it's a little more complicated, so we can throw it in with the other documents. And then in the valuation case, right, we're going to assume this is the value of that first term without the overhead in the evaluation of the event, right, which will be the probability that we just calculated, but with this prefix r. So this, in this case, is r. And we need to pass the event that happened, which is the lambda I. And we would like to do this, but we would like to do this, but this would entail using lambda I as a prefix. Okay, but like I said, that's a challenging thing for many reasons. Okay, so we're not going to do it that way. We are going to instead need to go piecemeal. So what we do is loop over the words in this case, right? Consider the probability of the occurrence of the first word, and then we can pass the word in the recursive call, and that becomes our next R. So we're conditionalizing the word. Okay. So this works, but because you have to loop over the words, there's a higher complexity to it. Okay. All right. All right. So we're talking a little bit here about the nth occurrence problem. So, like I said, so you weren't here when I introduced this. Sorry, what's your name?
Hernan.
Sorry. So I introduced this function, right? Which is the probability of getting a complex pattern n times before or at t. Okay. So from this equation, we can also get the probability, just so you know, of I, something like this, which would be the probability of the nth event, right? But I won't go into that because it involves calculating not just this, but the probability of the, I can go into this, let's do it. So notice that the probability of getting lambda I dot exactly n t is going to be equal to the probability of lambda I n plus n, this probably is going to be bigger, t minus the probability of lambda I n plus 1 t. And from this, we can get the probability lambda I n t, that's the probability of the nth occurrence, the first occurrence of the nth occurrence, right, at t, right, which would be equal to the probability of lambda I dot n t minus the probability of lambda I exactly n t minus 1. So I'm using this notation, right, to mean exactly n occurrences in the interval up to t. So if you want to know the probability of the occurrence, the first occurrence of the nth item at t, right? This can be exactly nth. Maybe that's a little better, but it's the same. It would be this equation. That's a little bit of my algebra, but it might be relevant to understanding how to use these combinatorially when you try to solve a problem. Okay, so the nth occurrence, we want this conditional on an initial condition of a word. It should be wi dot 0. It's always implied dot 0 if I don't write it that way. We're going to loop over the patterns of lambda, right, for the times. So we can't have an nth occurrence in this case, right, in this area. So we don't need to consider that. We can, but it's going to come back to 0. And then the probability of W occurring for the first time at T prime, conditional on the initial condition, times the probability of getting n minus 1 in this location. Let's see if that works. That might need some rearranging. I threw it in there as an example of what we can do recursively with this equation, but maybe it's not quite right. This should be exactly n, I believe. This should be exactly n, and this should be exactly n minus 1. Yeah. So it shouldn't be greater than or equal to n in that case. It should be exactly n and exactly n minus 1. And then with the exactly n minus 1 equation, though, you should know, right, if we have the probability of lambda I dot n exactly t conditional on prefix W0, right? Then if we want to know instead the probability of lambda I n t conditional on W0, we don't want to consider an infinite sum here, right? So we're just going to take 1 minus the sum of n equals, let's say m equals 0 to m equals n minus 1 probability lambda I dot m exactly t. Right. So this actually is the exactly n form, but that gives us this, which will then give us the probability of greater than or equal to n by subtracting out the probability that is less. So you don't need an infinite sum, right? That's good. Okay. So what I intended to write is actually recoverable from what I did write. Okay. All right. Okay. All right. So this is one method of counting the probabilities of the patterns. They're in serial form, so the form that we had been using prior. I want to mention that there's two sort of celebrated works in this area, right? The first is the embedded Markov method, right, which was due to Fu. I can give you the reference on that. But effectively, he creates a matrix of matrices. So you have a pattern matrix, but the patterns are only the patterns that you're worried about. But it's the patterns at every location on the diagonal, and you're able to calculate the probabilities of the nth occurrence. It's like a tedious method. It does exactly what this does, but in principle, it's more efficient in some cases, and people like it more. I'm not sure why. Okay, so you should be aware of that. It's probably more efficient for a number of cases.
That method only works for fixed and works, right?
The embedded Markov method, that I'm not sure. I haven't investigated that. I know my method, you can alter to be for different size patterns. And the embedded Markov method in their presentation in the presentation I saw in their book around 2000, the book came out, they are able to, they presented initially with fixed length words. Yeah. They may in later chapters generalize that. And then the other work here is, so the question is one of the problem with the embedded Markov method is really the space. So notice they still consider overlap in their creation of the matrices. They have to, right? So the overlap and everything we discussed is relevant to their work also. But the problem is usually the size of the matrix you end up with, right? So you can get an exact calculation by their method, but you end up with using a lot of space, right? You use a lot of space in our algorithm too, if you want it to run efficiently, because you have to store a lot of previous results. So you memorize, right, the results as you go, and it runs a lot more efficiently that way. But that's the problem with the embedded Markov. So Newell, in a 2008 paper, right, addresses the problem of the space requirement by assimilating the problem to deterministic finite automata, right? And then constructing what he says, at least, is the minimal space required to solve the problem. I haven't verified that. I was in correspondence with him briefly, but he makes that claim in the title. I don't see an actual proof of that claim, even though it seems realistic given the paper. So anyway, those are two results you should be aware of in this area. Okay. All right, so that's our introduction to complex patterns in the IID and the Markov case. And then, right, their use in the basic valuation equations. We have discussed the nth occurrence distribution, which is when calculated in serial form. So the serial form is the Blum form, which I'm expanding on. Can be easily modified to solve the more general concern of running out of resources, I promise. So I'm promising you the solution falls out of this. So the general form, right, getting in the Markov case and in the binomial case, or where you are going to be able to get, right, a solution to the general problem for this. And my hope is I will spell it all out very shortly. That's my hope. Okay, so we're already almost out of time, and I haven't talked enough about AI. Sorry. So let me get to the AI directly. I think I've covered everything else, right? The use of continuous distributions potentially. I haven't covered the use of patterns in space. The problem with patterns in space is that you have to consider things, if you want to do it correctly translations of the patterns in space, right? And then they change their orientation with respect to the time horizon. Things get complicated, right, pretty quickly, right? So if you can avoid it, all right, it's better to do it in a different way. But obviously, if you're trying to model a person monitoring a monitor, right, a pantalla, then you're going to have to try to understand, right, those patterns also, right? And really, I think the exact methods probably will fail, like computationally in the end. But the exact methods will serve in proofs of goodness, right, for approximation algorithms. So you can expand on this for exact solutions, and then you would consider the exact solutions versus the approximations, and then you have approximations that work computationally, but you have proofs of that given their relation to methods like this. Okay. Okay, so I guess the last thing is AI, and it's really, so I'm not going to cover really what I'm working on, but I'm going to cover a problem with some models of AI. Okay. So there's let's start by considering just our monitor, right? So you have, suppose you have some very large set of patterns, right, which you know are relevant, and so they have some value. Right? They would launch missions which you have some expected value, right? Well, that's fine, but consider the monitor, right? So they're a person, maybe not necessarily watching a monitor. They have this in sort of long-term memory, right? And so they need to take patterns from long-term memory into short-term memory in order to use them in a timely fashion, right? So in a quick way. So it's very simple, right? So the idea is you're preparing for a test, right? You only have so much time to prepare for the test. You have to grab the patterns, right? Put them in the short-term memory, whatever you can jam in, or mid-term memory, right? You might have a mid-term memory, right? To have them ready when you go to the test, right? Well, you have to pick what patterns you have the highest probability of being on the test, right? And so you draw from LTM to MTM, and then probably MTM to the short-term memory, right? What you need when you see the pattern, right? But you have to prepare for the test by taking things out of LTM and putting them into MTM so that you can pull them into short-term memory when you are taking the test, right? Okay. Okay, so the question in AI would be how to do this rationally, right? So this is a little bit more of a theoretical question. There's an area called automated general intelligence. Sometimes it's automated, sometimes it's algorithmic general intelligence, right? Where you would want to know, right, what is the absolute correct way of doing this? Given you know the absolute correct way of doing this as an exact method, you can then go back and consider what would be a good approximation method and proofs, right? So there's a question here, what is the exact relevant way of doing this? So consider, right, if our patterns have a particular value, right, we would consider then a pulling them into midterm memory so that you can use them for the test. But you have to know rationally what you want to store here, because this is a bounded resource, right? You can't just pull everything in and have it all ready, right? And so you need to fit whatever can fit. You can fit in there, but you want to pick the patterns that have the highest value, right, for your project, which would be the midterm or some exam, any event, right, that you want to prepare for, right? And then you can use them in the event. Okay. So this problem is obviously relevant. So the idea would be, right, you have certain, these would be particular patterns, so words, right? And you have to choose a particular lambda I partition, right? Because you would do different things, different missions depending on the lambda I, right? And then you would use them for the event you're planning for, right? So this is a very general phenomenon, right? And in fact, you can model whole agency based on this, which you can model an agent where this is a very relevant thing, right? The very general architecture. So I'm just going to describe one architecture where this is potentially relevant. Okay. So one architecture is Bayesian, so Bayes nets. If you're familiar with Bayes nets, okay. So Bayes nets, you can usually draw. We're going to make this a directed acyclic graph, right? Of the events, right? So you notice, and you'll probably remember, right? Each of these are sort of variables, right? They have their own distributions, right? Well, now consider that you can expand this directed acyclic graph into words, where you have probability transitions between the words. So it's just a Markov model where this is effectively a representation of a particular lambda. So if you're modeling an agent based on Bayes nets, in particular directed acyclic graphs, which are usually in the realm of causal learning, right? There's a professor, David Danks at University of California, San Diego, who argues for using directed acyclic graphs as a model of agency. He bases his work mainly on the work of Judea Pearl at UCLA. And if these are your representations, right, in the end, and you have to use them for prediction, right, you run into the same problem. Because these are just lists of words with probabilities, transitions between them, right? And so you'll have a whole set of these, right? And you have the same problem. And if your nets, so individual nets, right? So you'll have different nets, and this is just not equal to this, but you'll have different things of this form, right? Diagram 2, diagram 3, right? So if the question is, you learn these Bayes nets, right? But then you have to prioritize them for your use in an event, then you have to consider all the mechanics we just did, right? If you want to get it exactly right. Otherwise, yeah, there are approximations, but there are approximations. So within AGI, if we want to model an agent, something like this, right? Then with this Bayes nets architecture, where they learn individual representations of Bayes nets, but then can combine them in ways, right, to make plans and make longer predictions, right? Then you have all the same issues if and when these diagrams overlap with themselves or with other diagrams, right? If they do, if this variable y also occurs in another here, right? And this variable z occurs in the same order in this diagram here, right? Then you're gonna have an overlap problem, and it's everything we just discussed. And nobody talks about that. I don't know anybody that mentions that, but it's not a solved problem within Bayesian architectures. In fact, the person that wrote the book was surprised when I told him. Yeah.
You can that way improve the efficiency because you are considering the overlapping. So
Yep.
probably
In principle.
some patterns are more.
Yeah, in principle. There are certainly architectures where it will matter and other architectures where it will matter less. It always matters somehow, but if it doesn't, it's possible that in some architectures it matters too little to care about, but in other architectures it'll matter a lot, right? So getting a grasp on this problem within the Bayesian architectures has not been done. So I hope it falls out of some of the work that I'm doing, but realistically I'm working on an AI project which is based solely on patterns as it is. And these are just one representation of patterns.
That's
Does this
makes me
make sense?
think about.
Does this tie in with AI enough for you? I have more to say, but we'll
It's very tied up with the large language models.
Sure.
This-
so
all of this is
tokenization,
related to
I
language
think
models,
about tokenization to select which pieces of words are more useful to encode. For, in particular, the new models, the small language models that have a reduced vocabulary. So this is relevant
Excellent.
to optimize the set of.
Look, I know this is all relevant. So what we have been calling, right, letters, right, in our domain, right? So our alphabet, right? So A, B, C, D, E, right, are actually just words also, right? Which makes what we call words just phrases, right? And so all of this is relevant to the language models.
In large language models, the tokens are small chains of characters.
Mhm.
Strings.
Yep.
It's just like this.
Yeah, if you want to help me apply this, just cite me and I'll be happy. Because I know it's relevant to this. I know it's relevant to biology, which I don't say, right? And so there's plenty of relevance of this too.
Maybe this could be used also in encrypting and disencrypting information, like for faster information.
Again, there are areas where I don't want to step because then I just get in trouble and I can't do my research easily. But yeah, encryption and decryption, it's related to compression, yes. Because if you have, right, remember I showed you if you had 101, 1001, 1001, 1001, this is a pattern with more overlap, right? Because it has this periodicity property. It's also, so it has more overlap, but that also indicates you can compress it, right? Because this is just a repetition, right? And so it's a more compressible string, right? So it's the overlap issue is relevant too.
Compression algorithms exploit overlapping.
Yeah.
They build a vocabulary considering overlap.
Yeah.
I don't know if it is optimal in this sense.
Yeah, I don't know either. I know there's,
Compression.
it's relevant. No, compression is related closely to information, which is related closely to machine learning, right? And that full story and how it's related to the working patterns, I don't think has been told appropriately. Right? And so there's a lot more work to do in that area. Yeah, I didn't say anything about large language models, and I know that's the rage, right? But there's obvious applications. We're talking about words and strings, and it's clear that there's relevance here. At a minimum, right? There's relevance in the sense that the basic algorithms, given even a uniform distribution, give you what amount to an a priori distribution to use in Bayesian methods, right? For the approximation of probabilities, right? In Bayesian learning. So at least that is relevant, right? So anything else you guys want to ask? You can ask me after. All right, thank you guys.
Thank you.
Thank you. Very, very interesting.
Great, thank you. If you do want to contact me, I don't really have I have a phone, he's got it, but it's only WhatsApp. So these are some of the better ways. And the finance paper is at csschroeder.com, right? That's just sort of the initial foray into publishing in this area. And I'm sitting on a lot of work at the moment. But if you want to reach out to me, you can use cs at csschroeder.com or cs@3of.com. Okay?
Okay.
All right. Thanks, guys.
Yo les paso el contacto.
Perfect.
WhatsApp, ¿seguirás usando?